afternoon?
It is for me because I already had one class, so
Oh, nice.
that makes it
Good
afternoon.
afternoon.
It's afternoon
I
somewhere.
just finished my coffee, so.
Oh, good morning then. All right, how is everyone today?
Good. Not too bad.
Cool. Had to get up at 7 for the first time in a year. Wow. Okay, that's cool. Um, yeah, if you can sleep in, go for it. Um, yeah, I played with my snooze this morning for the first time in a while. So that's interesting to get used to. Um,
I remember coming into office hours. That was probably the earliest I've woken up since I started at Clark.
yeah, yeah. Um, Sometimes I do like 7:30 office hours too, and that can be harsh.
I'll say it's harsh, but it was definitely worth it.
Oh, good. All right, go ahead and send me an attendance note. Let me know you're here in the start here. Um, and what I'd like to do today is start off by going over ODP 410, the one you just finished, and look at that in terms of passing values to functions. And then I want to move from there, talk a little bit about pointers and arrays, and work towards moving strings from one function to another. So how we can pass a string argument to a function, and that's going to be what you need to do for ODP 411B. 411B is similar to another ODP you already did. You're parsing a string to make sure it contains an integer, and you're returning a value based on what you find. But the difference is that instead of taking a command line argument, we're writing a function that takes an argument as a function argument, takes a string as a function argument, and then parses that using scanf. So lots of details to build up there. All right, so let's do a quick look at ODP 410. So this was a pick function, takes an int, returns an int. And I usually give you the prototype for these functions. When you actually write the code, right, you call this argument whatever you want. It's got to have a name so you can refer to it. So here's one approach to writing that pick function. Takes an argument that I called n, because that's what I called it in the ODP, so that was easy. And the way I decided to do this, I made another integer r, which I set equal to n mod 4. And then I said if that's equal to 0, let's return a 1. Otherwise, let's return n mod 4, which was just r. So that would work for assessing ODP 410. But there are a lot of ways you can write this, right? So for example, instead of setting n mod 4 into r, I could have just said, you know, if n mod 4 equals 0, return 1, and then return n mod 4. That would work exactly the same. It would probably compile to something that looks exactly like this in the mind of the computer. Instead of saying if r equals 0, I could have said if r equals 1 or r equals 2 or r equals 3, return r. And then here I could have said return 1. I could have used an else statement if I wanted. I could have used a switch and switched on r, and if it was 1, return 1, 2, return 2, 3, return 3, default, return 1. A lot of different ways you can do this, and again, the way that you decide to organize the logic, I want that to be a way that makes sense to you. So don't get bogged down with what is the right way to do this. Okay, find a way to do it that makes sense to you, and that's going to be the best way to be writing this. So some version of this would work for ODP 410. All right, so this function pick, we can declare it like this. So for us, we put this in a separate file, like pick.c. And this is the function declaration. This is the function, this is where we actually write the function, right? But in our main program, assuming we're not going to put this code inside main.c, we need to prototype the function. We need to say something like integer pick parentheses int. And that's the function prototype. This goes by other names. Function declaration is what I call it. It's probably not the best term for it. But the essence of this is the actual code that makes up the pick function. This says what statements comprise the pick function. This does not. This just says, you know, what does pick look like from the outside? This is your system diagram, your 40,000 foot view. Here's the inputs, here's the outputs, with no detail of how those inputs get changed to outputs. This is what describes how the inputs get changed to outputs. So in pick.c, we don't need to make a prototype because there's nothing in here trying to call pick. Now if we had another function that tried to make a call to pick, then we would need to prototype that pick function. So anytime that you're going to use this function, you got to have a prototype somewhere in that file, preferably before you call it. And then this would be our usual main that would do some stuff, and at some point, you know, it might say something like x equals pick parentheses y. And presumably y and x are both integers, and the linkage here is when the code executes, it gets here, it says, okay, I'm going to call a function pick. It looks at the value of this expression, right? So the buzzword is passed by value. So it looks at the value of y, and then it starts executing this code, but as this code executes, the first thing it does is it sets n equal to whatever this value is. So if there's an integer y, it'll find the value of that integer and set n equal to that. If I did something like, you know, pick parentheses 2 plus 3, it would calculate 2 plus 3 as 5. It would set n equal to 5. So passed by value means that the actual value, if this is an integer, the numeric value of this thing in parentheses, n is set equal to that. And then this code runs. And if I do something in here like change n, right, that has no effect on y. If I change n, I change n, right? But n is not associated with y up here in my main program, right? It's the value of y that got passed to this function. And that value got used because in the beginning of the function, n got set equal to whatever that value was. Ah, excellent suggestion for that if statement. Yeah, use a hash in a server. That would be double plus good. Alright, so your code runs, it's using n, it's doing its things, it's doing your whatever. And then at some point there's a return statement. And again, the value of this is calculated, and whatever that value is, that basically takes the place of this. So if I say x equals pick, the end result is x equals whatever value was in this return statement. And if there was some other return statement that executed, whatever the value was in that return statement, that's what this would be, and x would be set equal to that. And if I say something like, y equals 5 times pick of, 12, what does it do? This is a 12, it sets n equal to 12, it executes that stuff. When it gets to return, whatever the value of this return expression is, that becomes this. It gets multiplied by 5, it sets y equal to that. So very mechanical. And kind of a side note, but related to this, in general, our functions don't print things unless that's the purpose of the function. So the printf function, it's obviously supposed to print something. It's in the name, right? But the square root function, for example, does not print anything, right? And that's good because, you're writing the square root function. How do you know how somebody wants to print this? What format should they print it in? Should they print something before? Should they print a new line after? That's not the job of the square root function. The square root function's job is take a double, calculate the square root, return the double to the caller. And if the person who's using the square root function wants to print the square root, they can write a printf statement. So same thing on this ODP, right? The description of the pick function was take an integer, call it n, and return either n mod 4 or the number 1 if n mod 4 is 0. And no prints anywhere in sight. Alright, so that's how we pass integers. ODP 411B, we're going to pass a string, and strings are different from integers. So let's talk a little about strings, arrays, and pointers. And the way I'm presenting this here will probably be a little different from how I presented it in the first class. So if you want a different presentation, you might find it by looking at the lecture video from 10 o'clock. But we'll see how this plays out. But typically when I'm lecturing on the same subject 2 classes in a row, right, the way I describe it in the first class sometimes helps me think about it differently, and I'll come up with a different description in the second class. So you can find 2 presentations sometimes. So let's think about what happens when we say pick n, like r equals pick n. All right. So here's a general tip for programming. Keep thinking about the machine. And yeah, as a programmer, you're working in the domain of software, you're writing code, you compile it by saying GCC and so on and so forth. We're not doing, protoboard development, we're not making traffic light controllers, we're not drawing state diagrams, but we are manipulating a physical machine. Right, we're interacting with something that has, logic circuits and a state machine and things like that. And the more you can kind of keep in the back of your mind, or maybe in the front of your mind, what's going on at the hardware level, the more some of these software concepts will make sense. So even though you're a programmer and you're doing software, don't disregard the hardware. Particularly with C, because C is so close to the hardware level that keeping the hardware in mind will help. Let's see, question. So stick program can accept any integer bigger than or equal to 20, so it's limited to 2 billion. So you can assume I won't play with more than 2 billion sticks. And if you just make an integer and the input number is not beyond 2 billion, it'll store just fine. All right, so I'm going to say pick n. So somewhere there's a memory, right? And there's a CPU, and there's an I/O subsystem, and these are connected to the CPU. And what is the memory? It's a bunch of storage locations. So think flip-flops from Engineering 250. And if we think of our memory as, sometimes we think of it as being 8 bits wide. but it's probably, you know, more like 64 bits wide. But it's a bunch of things that can store ones and zeros, okay, like flip-flops. Different technology, but same end result. We can store ones and zeros in here. The way this memory is organized, though, is that each of these locations, you know, can store multiple bits, and they have addresses. So we could start with address 0, 1, 2, 3, and maybe here's address, you know, 100 and 101, and so on and so forth. And there's some machinery that basically lets me say, hey, tell me what's stored at location 101. And it will go into here and it will read the values of these storage locations and send the contents to me. And if I say, hey, store a 5 in location 3, it will look at the storage locations for this element 3, and it will copy the value I asked it to save into each of those storage elements so that I store the binary value of my number. So when I call something like pick n, well, before I can do this, I have to say something like integer n. I do that in my C program. And at that point, the compiler does the following. It says, hey, I'm going to need to store n in memory somewhere. So it decides where to store n. And maybe it says, you know, I'm going to put n right here. And I put it at location 101. And this value right in here, this is going to be where n gets stored. And the compiler doesn't do that by itself. It actually happens with the linker, but we'll keep it simpler. So when I say integer n, someone makes a decision, says, okay, I'm going to store n at location 101. Next time I run it, it might get stored somewhere else. But let's just say it's stored at 101, right? Now what's stored inside memory location 101? No idea. If I don't initialize n, and I try to use the value, I'm just going to pick up whatever happens to be in memory. So I would do something like, say, you know, n equals 7. And at that point, the code that was generated by the compiler will execute, and it'll say, okay, let's take the number 7. Let's store that somewhere in memory. Where should we store it? We should store it wherever this variable n is supposed to be stored. And n is supposed to be stored at location 101. Okay, so I'm going to put a 7 into these flip-flops here. So it'll make, you know, a 111 and then 29 zeros. All right, when I say let's call our pick function, what does it do? It goes to location n, location 101. It reads that 7, and then it somehow passes that 7 to the pick function. And when our pick function starts to run, it will take its variable n, which is somewhere else in memory, set that equal to 7. All right, so that's passing integers. What even decides where to put the memory addresses? It's largely the linker. So after you've got your objects and you're building an executable, that will sometimes decide where things get stored, because it may be taking programs from different locations. But the more honest answer is these things are stored in a section of memory called the stack. We'll talk about stacks in winter term. But that means the actual location in memory changes each time that you run. And it just kind of depends, you know, what else in the system is using memory. And wherever the next chunk of memory is that's available in the stack space, that's probably where n's going to get stored. And it's a cool, mysterious aspect of where operating systems and executable programs kind of come together. All right, so this is not too bad with integers compared to what happens if we have arrays. So suppose I say integer x bracket 10. All right, so this is an array. And an array is a way to create, you know, effectively 10 variables without having to say integer A, integer B, integer C, right? And I could make 1,000 variables by just saying integer x bracket 1,000. And once you do this, you have this set of variables that we can refer to as x bracket 0, x bracket 1, and so on, up to and including x bracket 9. So there's basically 10 variables. But they're not completely unrelated to each other, right? They're related to each other because I can access each of them by saying x bracket something, but they're also related because they're stored in consecutive locations in memory. So in memory, once I say x bracket 10, what we'll find is that somewhere in memory, there'll be some place where x bracket 0 is stored. The next free spot in memory will be x bracket 1, x bracket 2, and so on until we get to x bracket 9. Now if these are integers, they each take 4 bytes. So depending on how you're drawing your memory, if this is only 8 bits wide, there'd be 4 locations for x0 and 4 for x1. We don't need to worry about that. But these 10 variables are stored one after another in memory. Which means when I said integer x bracket 10, one thing the compiler or linker had to do was find 10 locations in memory that it could use for x. So it found some spot and it said, okay, well this chunk of memory right here is available. We're going to store your 10 values of x right here. The other thing it does, and this is one of the really weird things about C, is that x is given the address where that first number is stored. So let's say this array started at location 240. And since this takes 4 bytes to store, then my next number would be at location 244, and then 248, and so on. So when I say x bracket 10, this would actually set x equal to 240, the address where my first x got stored. And that's the weird thing about arrays in C, right? So when you make an array like x bracket 10, x is actually the address where that first array element is stored. It's the address of x bracket 0. So let's put a little bit of code in place at this point.
So,
Yeah.
X bracket 0, is that saying start at the first spot in the array, or is that saying only take that first element?
So x bracket 0 is the first element in the array.
But are you pointing to the first element, or are you saying this is what I want you to use in that function? Or will it actually, like, can you increase the value of x to get different values for that function?
You actually could do that. It's a little awkward to talk about right now, but yes, x is, in this example, x is actually equal to 240. But if I treat that as a pointer, it's pointing to x bracket 0. And if I changed x to 244, it would be a pointer to x bracket 1.
Okay.
All right. Is there a way to influence where memory is allocated, say allocating a specified block of memory just to the program that the program may or may not be useful? Yes, there is to some degree, but it's a little hard to predict sometimes. And you can start playing games by printing out addresses of variables and start trying to understand how things get stored in memory. For example, if I say integer a comma b comma c, where do those get stored in memory? Is it a and then b and then c, or is it c and then b and then a, and so on? And it depends on the compiler and the linker and the operating system. A lot of things are aligned to multiples of 8. So if I'm going to declare one character and then I'm going to declare an array of integers, if the character comes first, there'll be a gap, so that when I start my array of integers, it's at an address that's a multiple of 8. And this is all like the really good, mysterious, under the hood stuff that makes operating systems work so well. What does an array typically look like within a stack? I am not going to address arrays of arrays yet. We'll get to those tomorrow, I think, when we talk about car star star. Well, let's stick with single dimension arrays right now, because two-dimensional arrays in C are even weirder than one-dimensional arrays. Does C use a terminator to show where x bracket ends? No, it does not. And this is another thing about C, is that there's no inherent array length associated with arrays. I might have spelled inherent wrong. If we're using arrays of characters, we decided, you know, nobody's going to want to store character 0, right? It doesn't look like anything. If you look at the ASCII chart, it's not a printable character. So we just decide when you store an array of characters, we'll put a character 0 at the end, as an easy way to know how big the array is. But there's no value, there's no integer that we could designate as marking the end of an integer array, because theoretically any possible integer value could be part of your array. So if I decide I'm going to use a -1 to mark the end of my array, well, if my array is grades, that works well, because I'm not going to have a -1 grade. But if my array is temperature readings, what if I read -1 degrees, right? I might think that's the end of my array and it's just a piece of data. So in C, there is no way, in a pure C implementation of a program, there's no way when your program's running to know where an array ends. And so we always pass around lengths along with arrays. And so yeah, if you try to read x bracket 11 or x bracket 10, you potentially get into areas of memory that are outside what you want. So let's play with this. And my landlord may be popping up in a few minutes, so I may have to go answer the door, but I'll be back. So let's do an integer x bracket 10. And let me give some values. Let me just set x bracket 0 equal to 11. And let's print out the value of x. Now I'll get a warning from the compiler saying, hey, you're trying to print an integer, and you know, this thing over here, x is not an integer, it's an array. But I can still run this, and it gives me some weird number. Looks like almost minus the square root of 2. And it's different each time. But if I print x bracket 0, right, that's going to be well behaved. Right, it's always going to be whatever I stored in x bracket 0. So let's put this in a loop. So let's just set xi equal to I plus 1 squared. Alright, so x0 is still 1, that's fine. But we've got, you know, this weird value for x itself, which is changing. If I print x9, right, that tells me x9 is equal to 10 squared, which is 100, that's fine. If I print x11, I get some weird number. And that weird number changes each time that I run. If I print x10, I also get a weird number. Well, let me compile. So we're just picking up, you know, some random location in memory. If
So
I print
it's
some,
not letting you can't access element that's not in the array. It's just going to give you weird numbers.
it's just going to give you weird numbers because it really has no way of knowing that I only declared this thing to hold 10 arguments at runtime. At compile time it knows, but at runtime, all bets are off.
Okay.
So if I access some really bizarre location, I'll probably segfault because element 122 blah 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 doesn't exist. It's a location memory I can't touch. So this X that I'm printing, right? This is supposed to be the address where this array is stored. So if my array is starting right here, X should be the address, right? And if you want to print addresses in C, there's a special format you can use. You can use %P, P as in pointer. And that'll do two things. One, it'll format it in hex. And two, it'll know whether we should be printing a 32-bit or a 64-bit number. So this should get rid of our error, our warning, and I'll still segfault because I'm printing a weird value. But here's the address where my X array is stored. It's at 7FFE9C21B880. And each time I run it, I get a different address, but it's generally a 7FF followed by some other stuff. And that's what we call stack space. That's where the stack on this particular architecture is set up. It starts at 7FFF, FFFF, or something close to that, and it decreases. Yeah, you could take that weird value that we were getting or this value and use that as a pseudo random number generator.
So if it starts at 7 FFFF all the way to F, that means there's quite a few things on that stack there, right?
There are, but the memory usage is not contiguous. So there's stuff at addresses starting around 0 that get used often for executable code and so on. And that grows to higher addresses. And then there's stuff around 8000, etc. that starts decreasing, and that's where stack space goes. And then there's stuff around like hex 555 something, which is what we call the heap. And when you use things like malloc, that's where that comes from. There's a lot of gaps in there, right? It's not like everything.
What you're storing, or what?
It's based on what you're storing. It's based on how much memory you have in your machine, how much virtual memory the operating system has set up, and so on and so forth.
Okay.
And this is a combination of compiler, linker, and the loader that's actually taking your code and preparing to execute it in the operating system. And it's a fun, hairy mess.
Is that something that you need to know where things are stored? Is that something that's going to be, like when you're writing a program, you're going to have to know exactly where your stuff's going?
For this class, no. But in CSE222, the answer is going to tend to be more yes. And we're not going to know ahead of time where something is going to be stored in memory, but while our program is running, we'll be looking at it step by step using a debugger, which we'll play with this quarter. And we'll be making memory maps, right? Things like this, but in a lot more detail, that may show us, my structure starts here, and this piece of it has this number, which points down here. And when I go to that location, I find, this variable and so on. And we'll start tinkering with the memory kind of barehanded. And that's where data structures gets really good. That's where the real power of using data structures will expose itself. And once you've gotten that stuff, you've got, complete control over the whole machine. And so usually on the other side of CSE222, people come out and they feel very different as a programmer. You come out with a much more solid feeling. There's less mystery about, I don't know why this works, but it works, so I'm just going to do it. We'll actually demystify a lot of that stuff.
That sounds fun.
I think it's the funnest course, in the sense that it really sort of like explains this and gets you to where you can work with it at a very low level. But 223 is a fun course because then we get to use all of this stuff that's already been built for us in Java. And we can make GUIs and games and networked applications and stuff like that. So they're all good stuff to look forward to. But we'll have fun in 224 too. All right, so if we want to pass an array to a function, we do it almost in a way that looks almost the same as our pick function. So let me just write some code, and then we'll talk about why this code does what it does. So I'll call this pass. All right, so let me make a bogus parse function. And the README will say, you know, your argument should be a car star. And we'll see why that is. But this is the prototype for the function. And I'm just going to do something like, you know, car temp 120. And let's read something from standard in into that. And then I'm going to, you know, result equals parse temp. And I'll print out result. All right, so we'll say enter a number. So we'll enter a number, we'll use fgets to get that, we'll call a parse, okay? I'm not going to write the parse function you need for the ODP, we're just going to write a bogus parse function. Just to see how we pass an array of characters, right? Temp is an array of characters, that's also called a string, and we're going to pass that to our parse function. Now when I declared my array of characters up here, I did it the way I always declare an array. I said character, name of the array, bracket, and the number of things I wanted to store. That's not going to change. But in our function, I'm going to declare my argument to be a character star. Let me call it something like input. Doesn't matter what we call it. Alright, so here I can do something like, you know, scanf, that string, %d, and then address num. So num's an integer. And I'll scan that input string as an integer, save that into a variable num, and I'll just return num. Let's do num times 2, just so we know we're actually getting an integer. All right, so here's a good sort of template for passing a string to a function, right? Up here in the main program, nothing has changed. We declare our array the same way that we've been doing it. We use fgets the same way we've been using it. But when we call our function, we just put in the name of the array. And remember, the name of the array, x, temp, whatever, is the address where the array begins. So when we call parse, what's the value that we pass? It's the address where the array begins. And down here, the argument named input will be set equal to that address. Well, if input is the address where our temp array begins, input is basically our temp array, right? It looks exactly like this thing up here. And so whereas before we would have said, you know, scanf temp, down here we can say scanf input. Well, that is doing an scanf on temp because input is the same as temp. Now, why am I declaring this as a car star? And sometimes it's easier to think of it like this, right? Input is a variable of what type? Type car star, where car star means a pointer to a character. I'm declaring it like this instead of saying car input bracket 120 because I don't know ahead of time how big this array is going to be. Right? I'm writing this general function which I say, hey, this will take your input and parse it as an integer and multiply by 2. I don't know what the size of the array is you're going to pass to me. So if I say car input bracket 120 and you did an array of bracket 10, right? then it's not the same size array. So declaring this as a char star is the right way to receive an argument that's an array. And if I wanted to receive an array of integers, I would say int star input. And I like putting the star next to the variable, but it makes no difference to C. All right, so this should work perfectly fine, barring syntax errors, which are almost always present. So enter a number, 234, and the result is 2 times that, 468. And so this is all we need for ODP 411B, which we're going to take a look at right now. But the more you can sort of understand in general what this is doing, right, the better, because we're going to do this kind of thing a lot in this course and then in 222, where we declare an array, we pass it by just giving the name of it, but then in our function that we're passing it to, we declare the array as a pointer to whatever type of thing is in the array, a char star, for example. Alright, so let's look at the ODP. So you're writing a function named parse. Hey, what coincidence. And it takes a char star, which is an array of characters, which means it's a string, and it returns an int. Alright, and you got to do something very different from what this code is doing, right? My parse function is bogus. It's scanning a %d and it's returning 2 times the number. And you know, if I type in haha, it will, you know, give me back some number. So you got to do something different in your ODP. What you need to do is take that argument, parse it using scanf, right? And parse it to see if it contains exactly an integer. And if it doesn't contain exactly an integer, if it's like haha, or it's an integer followed by some extra stuff, that's considered illegal. You return a -1. If it's an empty line, that's illegal. You return a -1. But if it contains an integer and no extra stuff, right, then you go ahead and you convert it to an integer value. And if that value is 1, 2, or 3, you return that value, 1, 2, or 3. Otherwise, you return a -1. And your parsing is only done with scanf. Don't try to parse this yourself. So for example, if I type a bunch of spaces and a 2, it should interpret that as a 2. Right? scanf will return it and say, yeah, that's a valid integer, go with that. Okay. But if I were to type in, you know, a 2.3, scanf should tell you, yeah, there's an integer, but there's some extra stuff. You should record that as illegal. If you just use the result from scanf, you'd end up with a 2. So do the thing we were doing the other day when we parsed the command line argument with %d followed by %s, and then saving that %s pattern into some extra, and then checking the return value. The only difference on this one is instead of processing a command line argument like argv bracket 1, we're processing an argument to a function. For example, this argument input. So you're going to do your scanf. Whatever you call your input array, %d, %s, whatever you want to call the variable that you'll save the integer into. And then this big character array with like space for 100 characters or so that will pick up the extra stuff. And then if r is equal to 1, that's a good parse. If r is not equal to 1, that's a bad parse. Return a -1. If it's a good parse, then you check the value of num. If it's 1, 2, or 3, that's good, return the value. Anything else, it's an error, return -1. So yeah, take a string, test the value, test the return value first of all, make sure that it is a number. And if it is a number, then make sure it's between 1 and 3, and if it is, return the number. Any other case, return -1. So you got to write your own test bed for this, and there's a lot of different ways you can do that. You can do something like what I did here, where you get input from the user and you call parse. But you can also do things like you could just say, you know, integer result equals parse 55. And when you put things in double quotes inside C, the compiler will make an array of characters for you. This will make an array containing a 5 followed by a 5 followed by a null terminator. And it will find somewhere in memory to store those characters. It will store those characters, and then the address where the first character is, that's what this is equal to. It's a number. It's a location in memory. It's exactly the same thing as calling parse parentheses temp, except here I'm just saying, hey, make a string equal to quote 55, pass that to my parse function. And if I do that, what did I call this thing? Pass. If I do that, right, it passed to 55, it parsed it into the number 55 multiplied by 2, and there's my 110. So you could hardwire a bunch of tests like this, right, and you can do this in one line. Right, so now I've got 3 tests of my function there. Oh, I messed up bad. Right, so there's my 3 test cases. So you can hardwire test cases, you can read them from standard in using fgets, you could use the command line argument and you know, parse argv bracket 1. It's totally up to you. But design your own, you know, set of tests and exercise your parse function. And then once you're pretty sure your parse function's working correctly, link it to the test bed, go ahead and assess it. And I think there's 20 or 30 or 40 tests that the assess program runs on your function. All right, and this is due at 10 o'clock tomorrow, so definitely work on this, you know, before office hours tomorrow. Don't come to office hours and say, how should I start this, right? Because that's not going to get you a lot of benefit. But definitely work on this, and if you can't get it done, if you're completely stuck, you can't figure it out, no matter how many times you look at it, right? We can work on it in office hours and go from there. Give me 1 sec. Send me an attendance ping while I'm gone. I'll be right back. Anyway, there's the walkthrough list. No, we're here. That one.
Okay.
And we got the shower door working. It just come off the tracks.
Oh, really?
So the shower door is fine.
Oh, it was right now, it's fine.
Yeah. I'll be done in 1 minute teaching.
Yeah, I think you forgot to sign, right here.
All right. You should be good. So have a good afternoon. I will see you tomorrow. Good luck on the ODP.
Thanks.
All right. See you tomorrow.